me just start that again, right? So residuals talk about the difference between the observed value in a data set and the predicted value in a data set, which is, it's wordy. But basically, if you think back to what we did in Desmos, we got this computation for f of 100, which was the y value when x was equal to 100, right? That's what we call a predicted value, all right? If there was some value in the table for 100, for the x value of 100, that gave an observed y value. So let's say the table said 100 corresponds with, let's say, 330. Then we'd have two different values for y corresponding to the same x. So when that happens, we subtract the two in order to determine what's known as a residual, which is the deviation from your prediction. So the observed value, what really happened and what should happen based off of your model, all right? So this whole table takes you through the process, but it's, you know, it's not really the most user-friendly thing in the world, because you look at it and it's like, oh, that's not really fun when you just throw a set of numbers at us and expect us to interpret it. So let me take you through an example in a second, but before I do that, let me just walk you through what a residual plot will tell you, right? So when we construct a residual plot, so we come up with a regression model. So we have our data set, we come up with the y equals mx plus b. So we have the regression equation. We use that to create the residual plot. Now that residual plot is either going to have a pattern to it or it's not. If it does not have a pattern in any way, that means that the linear model is appropriate for the data set, for the original data set. So if there is no pattern, to the residual plot, then a linear model is appropriate. All right. If there is some kind of pattern, then it means the linear model is not appropriate. All right. So it's the reverse. Right. So you can see below that, I break it down into different possibilities. We got the parabolic, you know, curved pattern. We got what we call a telescopic pattern, where it starts off tightly grouped and then it starts funneling outward from there. So it doesn't seem like in number 2 down here, it doesn't seem like it's a pattern, but that's actually called a telescopic pattern. All right. So if you look at a data set and see any kind of pattern, when you have a residual plot, then a linear model is not appropriate. So if there's a pattern, if there's something in there, you look at it and say, oh, look, a circle or a parabola or even a line, any kind of pattern is formed, then a linear model is not appropriate. But if it's all scattered all over the place, all the residual points are just kind of like messily scattered all over the place, then it's weird, but that means that a linear model is the most appropriate, right? So what we want to do is tackle an example where we can actually figure out what these residual plots are all about. So we're going to get this data into a fresh Desmos, right? And I think you want to do this as a fresh one. And there's a fresh one where that came from. So this one I'm going to title it residual, but I guess I got to put some stuff in it first. So let me get a table. X and Y, so 6, 9, 3, 8. Now you saw after I typed in, well, maybe you didn't, but after I typed in the 6 and 9, it tried putting in a 12 because it saw I was increasing by 3s. So again, you just got to be careful. Don't let Desmos do too much of the thinking for you. or these kind of data sets, there's a lot of dead air because it's like, you just got to type it in. But you see how heavily we're relying on Desmos here, and other forms of technology are coming. You know, we'll get into Google Sheets a little bit down the line, and GeoGebra. Well, we've done some GeoGebra, but these are some things that, you know, like it's strictly reliant on our ability to type in the data correctly. So if we don't do that, we're in a pickle, you know. So I'm going to take a look at the graph. Graphs are fun to look at. So this is what the data set would look like in its graphical form, right? So what I'm going to do now is I'm going to stop. I'm going to save it. And I'm going to call it residual. All right, so I have a graph ready to rock and roll. So, you know, I'm a student in the class. I'm ready to take a test. I see a question related to residuals. I'm like, oh, I got an app ready to rock and roll. All I got to do is change the data. So that's what we're looking at here. So plotting a scatter plot, you know, it can be as simple as a copy paste job, but when a question is asking you to plot it, it's implying that the points need to actually be plotted. So, you know, that's something to be mindful of. But I can tell you, and this is full disclosure, I'm not going to be asking you to make a scatter plot on the unit test. So forgive me if I get a little lazy here and just do a little copy paste, because I don't feel like typing it actually, or writing and drawing it. Honestly, it looks better than anything I could produce anyway, so. Make this a little thicker. I'll get rid of this straight line here. Yeah, look at that. All right, so that's what the scatter plot looks like. Now, we could put a linear regression model in here, but the idea is to make a determination of whether a linear model is going to be appropriate. You know, I don't want to get too far ahead of myself, but that's the general idea. So is there a pattern? Does the data appear to be positively, negatively correlated, or neither? It appears, so this is the x-axis, this is the y-axis. It appears to be a positive correlation. I don't know how strong that correlation is going to be, but it does look like if I were to slap a line on this, I can get a line through it. I got this little guy out of here that's out of whack, and that could be an outlier or an influential point, but it looks like I got the makings of a positive correlation, right? So that's just, I'm just throwing that in there, the line and the identification.
Professor, is it scatter plot or residual?
This is a scatter plot.
Okay, thank you.
So we need the correlation coefficient and the regression equation. So y tilde mx plus b. So y1. I'll never remember that the first time. y1 mx1 plus b. Fortunately, Desmos has a way of reminding you. It's not always the nicest way. It just sometimes doesn't do what you want it to do. Right? And so you know. It's asking for a correlation coefficient R. So here it tells me that R is 0.4 repeated. So we'll just go with 0.444. Right? It's a positive value. So does it support your answer to part it? Kinda. It's a positive correlation. It's just not a very strong one. So yes, but not strong. All right. So it's not a strong positive correlation. It's just a positive correlation. All right. If it were strong, it would be closer to 1. All right. But this isn't anywhere near 1. find the regression equation. Well, we already got that. So y equals the m value 1.546 x plus 25.845. You can go the whole way out decimal wise, put everything that they have there. I'm just going three significant. But if you wanted to put the whole shebang, you could. I'm not going to lose sleep over that. All right. Discuss any outliers or influential points by looking at the scatter plot. Well, that point at the x value of 20, right, that one there seems to be an outlier, right? But it's an outlier in the horizontal direction, right? So an outlier that's off the beaten path in the horizontal direction is an influential point. So that it seems that there's an influential point at, and I'll highlight it here, 240. I'm sorry, 2040. All right. So, and that's because it's off to the right.
Professor,
Hmm.
can you explain again why it's an influential point as opposed to an outlier?
Outliers are points that are off of the curve, but influential points are outliers that are deviating from the curve to either the left or the right. And because this point, the one that's in the box, is a deviation from the line in this case on the right, not too high, not too low, but too far to the right, that makes it an influential point.
So if there was a point like all the way down close to like the 0 on the right hand side, that would more be an outlier.
Yeah, exactly.
Okay, got it. Thank you.
No problem. All right, so the next part says remove any potential influential points from your data and recalculate your regression equation. Did they in fact make a significant difference to your regression line? All right, so that's a key ingredient to this, as opposed to some of the other problems that we've done. We're actually going to be removing points, so I'm going to clear that out. So 2040 was the value that needed to be cleared. Now, when I wiped out the 20, it took away the 40 that went along with it. So all I want to make sure, well, I want to do more than this, but I definitely want to double check that I deleted the right thing. So 30, 60, so everything looks good so far. Just making sure that I didn't accidentally delete the wrong thing. So the only value that I took out of my model was the 2040, the one that I thought was the influential point. I removed that, and I want to know to make a significant difference to the regression line. Well, yeah. I mean, the equation is so different, right? It's not even close, right? So the R value, they didn't ask for R here, but I'm going to put it anyway. The R value jumped to 0.785. So it went from, all right, there's a positive relationship, but it's not really that strong, to now it's kind of strong. All right. And the model itself, the slope went from 1.546 to about 5.099. I'll say 0.985. X plus 2.300. All right, so we're looking at a major change in the quality of the function. All right, it went from something that was kind of shallow to something very steep. All right, just by removing that one point. So very, very significant in terms of the change. Now we're going to learn hypothesis tests down the line that allow us to make a determination of whether or not something is considered statistically significant. But for now, we're gonna eyeball it, and we're gonna say yes. It's yes because R went from 0.4-ish to almost 0.8, so it almost doubled, right? And the slope and the y-intercept are completely different from what they were. All right. So that's an example of how we handle an outlier influential point. But now what we want to do is construct a residual plot and discuss those implications, because the residual plot is going to help us make a determination of the appropriateness of the linear model, right? So what I'm going to do is I'm going to create a new table, right? That new table is going to consist of the X values from the original table, right? So I'm going to just do a plus table. I'm going to type in the 6, the 9, and so on. I'm going to type in everything except for the 20, all right? We don't want the 20 because that influential point should have never been there. So we were told to remove it, so we removed it. All right. So this part is very, very strange. I mean, it's all very, very strange. But this part is probably, I would say, the strangest thing that we'll ever do in this class. What we're going to do is in Y2, because we have X2, you know, because we already used X1. So now we have X2. But what I can do is I can change that X2 into an X1. I can make that adjustment. But then you see what happens. It just wipes everything out because of the confusion. So that's like, oh, well, let me not do that. You know, I could leave it as an X, but it's like, fine, let's just leave it as X2. You know, but the Y2, what I want to do is I want to put in the right-hand side of my linear regression equation. So this information is what's going in there. All right. So, well, you know, check that. Let's leave that as Y2. I have a better idea. I'm gonna really let Desmos do all the work for us. All right. So we'll put in our Y values, the original Y values, the 30, the 49, and so on. I'm going to retype that. There's other ways to do this, but I think this is the way that's going to lead to the least amount of confusion. A little more typing to amount to a little less confusion. How about that? All right, so I got those values in there. All right, so it's the original data set without the extra 20, right? The 2040. So what I'm going to do is I'm going to tap into the next cell. So first you tap on the Y2 cell to kind of tell Desmos that you still want to work with the table. And then you tap on the cell adjacent to that, right? So I want another column, all right? And what that column is going to be is the computations that you're going to get by typing in the 5.095x plus 2.3. All right, so I'm going to type in 5 point, and it's kind of blurry here. It's annoying, but because when you're working with the app, it tends to kind of merge together. But I just expanded the screen, and it's a little bit better. But 5.0985. This I want it to refer back to x2. And then I'm going to add to that 2.3. All right. So a lot of weirdness going on, but all I'm doing is I'm having Desmos all in one. Oh, well, that happened. All in one shot. I'm just kind of scrolling so you can see it a little bit. All I'm having Desmos do is plug each of the x2 values into this equation so that it gives me all of the values that should be predicted values, right? And then what we have to do is find the difference between those two columns. Right. So what a lot of people can, thing to do is you can try something like this, y3 equals, and give it a name, but that ends up not working out. So it's kind of frustrating. But what I'm looking for is, let's see if I can get my display to work properly. I gotta go wider. It stinks, but that's what I gotta do. All right, so I have my Y2, and I have this column here with the 5.095 x2 plus 2.3, right? So if I want residuals, what I'm gonna be doing is I'm gonna subtract these values, these two columns. So there's a couple of ways to do it, but again, I think the easier way to do it is to just take the column headings and subtract them directly. So I would say Y2 minus, and then all the column heading for the column that follows. So 5.0985 x2 plus 2. Right, in parentheses. And we get this big old mess in terms of the graph, which is kind of aggravating, but that's the least of our worries. I'm trying to expand this so you could actually see it. It's actually working now for some reason. It wasn't working before, but this should be good enough. So again, just to recap, we typed in the original coordinates, X and Y. Then in my new column, or the third column, I took my regression equation, and like I said, there's shortcuts to it, but I think that the little bit of typing goes a long way. So we took our regression equation and replaced the X in that regression equation with an X2, because that's where in that first column all those X values are. All right, it's denoted as X2. So that gives us what are called the predicted values. So these are the predicted values. And then I subtract those predicted values from the observed values, right? The Y2 column, or the observed values. And so that's going to help me come up with my residual plot. And there's a lot of this stuff you can do by hand, and you can do it with other forms of technology. There's residual plot calculators and all that stuff out there. But this is a way, I think, and people don't always agree or don't want to agree, this is the way that's going to allow for the greater degree of understanding of the concept, for better, for worse, right? So we have to plot this information, and that's how we're going to come up with a residual plot, right? So I'm going to go back to my notes. I'm going to pop this diagram, this table in here. Oh, wrong page. So pop this page in here. And what I'm going to do is plot this column against this column. All right, because these are my X values and these are the residuals. All right. Now the X values, they span the lowest value of 3 to a highest value of 10. So I just need to come up with a reasonable scale that's going to get me there. I can start off at 0 and then max out at 10. So I'll call this 10 here. 5. All right, this is to allow me to plot all my X values. Now the residual values, they max out at the highest number is 27, the lowest number is negative 13. So maybe I want to go by tens there.
Professor, can I ask a quick question? For the residual values that you have up top, is it 5.0985x
plus 2.3.
Oh, minus 2.3?
So plus 2.3.
Okay, thank you.
No problem. So I'm creating a scale here that's going to allow me to plot all these points, but that, that's part of it where it's, like I have to account for a negative 13 and a positive 27, but I got a lot of values that are close to zero. So, that I got to be able to come up with something that's going to hit all those buttons, but it is what it is. So when I plot 6 against negative 2.5, so I'm going to have to ballpark that. That's going to put it like right around here. 9 against 1.1, that's going to put it around right here. 3 against 0.7, like around here. So very close to the axis. 8 against negative 0.7-ish, like right around here. Because I'm going by 10, so it's got to be really close to the axis. All right, 5, negative 2.5. 8 is going to plot with a 27 or so, something along those lines. 4 with a negative 7-ish. So you're in that neighborhood. 11, all right, that's one value I didn't include there. I got to go a little bit more. 11 is going to have a negative 13 or so. It's going to put it about right here. And then 10, negative 0.9 is going to be right around the axis also. All right, so this is my residual plot. All right, so it's x against the resids.
Sorry, what's the number you're using for B? The 2.3 number, because I'm getting slightly different results, and I'm probably wrong.
It should be 2.300 even, but I'll double check.
All right.
It's giving me a different number also.
Oh, dang it! It got cut off on mine.
Yeah.
Yeah, there we go. Yep.
Son of a gun, heck!
Yeah, so see, it changes.
Here we go.
It
Yeah,
changed everything.
here's more like
Yep. And I'm here throwing away my phone and getting upset and
it.
oh boy.
Oh yeah, I was looking at that too. Thank you.
No problem. Thank you. As it turns out, fortunately, I mean, this could have been so much worse because these values are still going to plot okay. They're going to plot to roughly the same location.
They were almost identical.
Yeah, so got lucky in that regard, but man, that could have been so much worse. So let me. And all right, yeah, but the graph's pretty much the same, so I got lucky in that regard. All right, but that's a residual plot, and the implication of this plot is actually pretty simple. I don't see a discernible pattern here. Right? I mean, I see points plotted near an axis, but I don't see anything like a parabola or a circle or anything like that. So I would say that there is no clear pattern. And so we can conclude that a linear model is appropriate. All right. Just we get all that background calculations, all that stuff that needed to happen. That's what makes this stuff challenging. And then also reminding yourself to save your work on Desmos because you don't want to type all that stuff in again, or at least you'll have the framework moving forward. But, you know, it's the kind of thing where it's like, man, this is brutal. But the computation part of statistics is the brutal part, you know, but you don't have to do any of it by hand. You know, imagine doing that, you know, like making a whole table of values, that'd be a nightmare, right? So G we can get rid of. We're not going to bother with that. That's kind of a particular type of problem that's like not really overly useful for us. But H is, it says a new job applicant scores a 9 on the aptitude test. The employer wants to predict his productivity level. So you got to go back and remind yourself what the variables are. But this is another prediction question. All right. So just going back, X is aptitude score, Y is productivity. So here I have an X value that's given, X is equal to 9. And we're being asked to determine the productivity level. Now, the good news is we already have that, right? When we created that whole big table, we got observed values and we got predicted values, right? So let's just go back to that table real quick. These are the Y values that correspond with the X values. Yeah, that's true. That's wonderful. But specifically, these are the Y values that happened. These are the observed values. These here are the predicted values. So if you have this whole table already taken care of, then all you have to do is kind of cross-reference and see, you know, they said an X value of 9. All right, so what does that correspond to in the table? It corresponds to a predicted value of 48.1865. All right, so the predicted value when X is equal to 9 is, I already forgot, 48.1865. And so that's a productivity level, because we always want to answer the question that we're being asked. All right, so we're able to make a prediction, but we don't have to go through all the machinations that we did before. I mean, we can, if you like that sort of thing. We can type in the linear regression equation, the 5.09852, the Y equals, I'm sorry, f of X equals 5.0985 X plus it was 2.3. So that's the linear model. And then we can evaluate it for when X is equal to 9. So f of 9. And you can see that we get the value. We did this already, but now we're tackling it using a slightly different strategy. All right. And so like we have this catch-all approach for finding a residual plot that we can now use for other things. Right. So, you know, there's a lot to it. It takes a lot of practice when it comes to the Desmos calculator, right? But yeah, it's very doable. You just gotta be patient with it.
So, Professor, this is my first time using Desmos and scientific whatever. If I don't understand properly how to use it, I'm screwed then.
Yes. Yes, absolutely. Unfortunately.
So I am screwed.
Well.
No, I'm trying.
Yeah, and that's why, especially with this course more than any other course, because it's so reliant on the technology, I always leave that one class session before a unit test to have the Q&A, so that when people do try to figure out the technology piece, because most of the time the definitions, carrying out processes by hand, that's usually not the problem. It's always the technology. So then we can kind of pick up the pieces, the class before the test, and we can put together a nice approach, so that when you do sit down to take the test, you're not trying to figure out the technology while you're also trying to figure out the math. Right. So the big takeaway here for a lot of us should be, let's spend some time this weekend trying to get the tech down, and if that doesn't work, we have Monday that we can talk about it, because I have no new material for you on Monday. It's all going to be review. All right. So like I was saying before, be on the lookout later tonight or early tomorrow morning for a document. I'm going to send it out on Remind, but it's going to give you all the details about the structure of the test. And it's also going to give you details about content that'll be on the test and what you're allowed to do and what you're not allowed to do and all that good stuff. Right. And so, and just some suggestions on how to prepare. Right. So just be on the lookout for that. And like I said, Monday, we're going to spend as much time as you want, because I don't have any new material for you. So when class starts, you ask me questions, I answer questions. And when you run out of questions, then class is over, but you can keep me going for as long as you need to. Right. So that's what I offer, because I know in this remote environment, we have lots of concerns that don't always come up when we're dealing with an in-person environment. But also on top of that, me not being on campus, and also even if we were physically able to be on campus, I still wouldn't be able to be on campus. I got the day job, and then I got the night job, all that stuff. So I always build in that one session before the test, because of the lack of office hours that I normally are unable to have. So that ends up being part of the office hour experience. All right. So I'm going to stop the recording here. I'll get the